All right, thank you everyone for being here. So the introductory remarks will be brief, so we can get right into the material. But so first and foremost, we're really lucky to have the lineup of speakers we have. So we're going to have Quantile, who's a world expert in statistical decision theory. Pierre Jacob, who's one of the finest minds in the Markov chain in Monte Carlo. Blaise is going to join us. He came from Europe, so I think he's catching up on sleep a little bit, but he's a world-leading expert in quantile regression, so we're extremely lucky to have him with us. And then Jose Blanchet is going to join us on the day after tomorrow, and he, of course, wrote the seminal papers on distributionally robust optimization and is going to tell us about that. Thank you also to you guys for coming. I know most of you flew in to be here, so we really appreciate that, and we're really excited to share what the kind of things we're passionate about with you. And then throughout, if you get a chance to thank Diana and Diane, they've done all the legwork to make this possible. We just kind of show up here today and talk about nerdy stuff. So when you get a chance to thank them, please do so. Okay, so you saw the schedule. The setup is for lectures every day. So Pierre, Pepe, and me will be lecturing every day. There'll be 2 lectures by Blaise, and then Jose will take his spot and teach the last 2 days. All right, so get started on quantile regression today. The idea is to sort of start from scratch. So introduce quantile regression. You'll see I'm very partisan towards quantile regression. One of the main points I'm going to try to push today is that whenever you do OLS, linear regression, for exploratory data purposes, really there's no reason not to do quantile regression. The sort of cost is the same, but the benefit is much greater in a sense. And the point being, instead of just getting access to the conditional expectation or a best approximation of it, you're accessing the full conditional distribution. And so as data analysts, we have extremely strong motivation to become nimble, to become deep thinkers in terms of quantile regression. And one of the important properties is going to be able to think about this in a modern way. So why do we like OLS? One of the reasons we like OLS is that even though the conditional expectation is almost never linear, when we use a linear model to try to study it, we get a best approximation in some reasonable sense. And we want to do that. We don't want to live in a world where we pretend that things are well specified when they're not. We want to ask what happens under misspecification, and we'll get a satisfying answer in that sense when using quantile regression too. So that's where we're gonna take it today. Okay, so let's motivate quantile regression and define it. So I want to do it in comparison with OLS because it's the natural competitor. Ordinarily, Square is going to investigate the conditional expectation, and that's great, but that's not everything. Quantile regression is going to investigate the entire conditional distribution, and that gives us access to much more information. If we're well specified, in a sense, it gives us access to all the information. Implementation is as easy as for OLS. Instead of solving a least squares problem, you're solving a linear program. So it solves very fast, and it's we can study it completely. We have a mature theory to study that. But then strangely, it's sort of not as common. I think it has to do with the fact that it's slightly more difficult to interpret. There's a lot of inertia in the econometrics curriculum, so it's not part in most places of, certainly not undergraduate teaching, oftentimes not even first-year graduate teaching. There's this thing that might be a little bit frustrating when compared to OLS, that you don't quite get a closed form for the regression coefficient. We'll see that we sort of do, and we'll provide an intuitive derivation for that tomorrow, relying on linear programming duality theory. Okay, so a motivating example to sort of try and convince you that you want to use quantile regression, that you could be missing the big picture if you only use OLS, and that has been historically it has been a motivating example. So that was presented by Gary Chamberlain, and Roger Koenker really credits Gary in part to this example for pushing quantile regression as a bona fide regression analysis tool, not just a robustness check via median regression for OLS. So the example goes like this. We're interested in the union wage premium, and we have union workers and want to compare them to non-union workers. What's the impact of unionization on wages? And so we're not making any causal claims here, we're just running a regression. And so this is 1987 CPS data. We have log hourly wage for a bit more than 5,000 men. There are some controls we're going to abstract away from that and just look at the effect of the unionization. And we're going to look at it separately for manufacturing and non-manufacturing. So think of interacting completely for that. And that's the table. Okay, so suppose you don't know about quantile regression, so you're like 10 minutes ago, and you only look at your OLS, and you have the effect of unionization in manufacturing and non-manufacturing, and what do you conclude? So very likely looking at your table. Right. Nothing really significant happening in manufacturing. In non-manufacturing, there seems to be a significant positive effect on average, and that's about what you can conclude. Okay, now you run your quantile regression, and you run it at different quantiles. And in a sense, it can still be self-explanatory. This is the effect on the 10th percentile, 25th percentile, and so on. And now what do you see? Yeah, it's decreasing. So first of all, we thought all the action was in manufacturing, but it's actually pretty boring in manufacturing. The effect seems to be slowly decreasing in the across quantile. There seems to be much more action in the manufacturing industry. So let's look at that. And then what we're saying, so it's decreasing across quantile. So what's the story here? What's happening? Well, first statistically and second economically. That's right. But what am I getting here? I'm getting that I'm getting the effect on the left tail, the 10th percentile, is a lot bigger. So the wage at the 10th percentile is increasing a lot more than at the 90th percentile. Even in fact here it's significant, but we're getting a negative point estimate. Okay, so this is how the wage distribution is changing. I'm bringing up the value of the 10th percentile, the wage distribution a lot more than that of the 98th percentile. So that's tautologically what the table is telling me. Economically, why is that interesting, or maybe what you were expecting? You can talk about unions even though we're at Chicago, it's okay. We'll not tell on you. So what do unions do when they come in? How do they change wages? Which wages do you expect to go up? Which wages do you not expect to go up? Yeah, right. It's about more fairness. It's about helping the people at the left tail of the distribution, and that's exactly what we're seeing here. People on the right tail doesn't help them. The union's not gonna fight to raise their wages, but the people on the left tail is gonna help them. And so the whole economic content was completely lost in the linear regression, but it was very well captured in the quantile regression. So it's extremely strong motivation for us to know how to use this method. Okay, is everybody digested the table? Can everybody read it? Yeah.
Could we also not capture the same thing by separating the data into the smaller or the lower wages versus the higher wages?
Yeah. So keep that question in mind because it's going to actually relate directly to how this table was exactly estimated. It was not exactly estimated by quantile regression, and there's a nuance that has to do with your question. So we'll get back to that. Also, of course, the other short answer is that if we think there is structure as to how the value of the quantile across x's, then that allows us to use all of the data at once instead of splitting it, and so we would want to do that then. But you'll see it relates directly to the slide that's coming up a little later. Okay, any other questions about making this table completely trivial, completely clear? All right. Okay, and another way I like to think about it, to really make clear what it is that we're doing when we're estimating a conditional Quantile, conditional Quantile regression function, is to sort of rebuild it from scratch. So if you think of a very, very simple example, so I want to run an OLS, I have X values and they're ordered but discrete, so I have 1, 2, 3, or 4, maybe years of graduate education, and then I have Y, some outcome, like money or happiness, and I have observations. And if I'm interested in the conditional expectation, then here it's very easy to estimate non-parametrically. I can just take the conditional expectation in each bin, and that's a non-parametric regression. So it's a scary word, but turns out to be easy in this case. And if I think that these line up on the line or almost on the line, then maybe I want a lower dimensional parameterization of this regression, and I can try to pass a line through these guys, and that's going to be my X beta linear regression, and I can estimate that by OLS. Okay, so this is why am I telling you this kindergarten story? Okay, so one more point. What am I estimating when I do that? I'm estimating the regression coefficient, that's called beta star, that solves this problem in population. If it's true that these conditional expectations lie on the line in X, then what I'm going to target is going to be exactly the conditional expectation. So if the conditional expectation is indeed linear, so if I'm well specified, then that will be the conditional expectation of Y given X. Okay. Let me just flip the order a little bit. So what does it mean to run a Quantile regression? Well, I can go through the same story. So this is why I wanted to be so pedantic about the OLS. I can pick up in each bin the 10th percentile, right? It's going to be lower. 10 percentile here, 10 percentile here, 10 percentile here. And if they think they lie on a line, my Quantile regression, for the true notation, I'm going to write Q0.1 Y given X. But if I think this object is truly linear, then that's going to be X beta, what beta? The beta that corresponds to the 10th percentile. And I can pick up the 90th quantile the same way. It may not be a perfect line, but I can try to approximate it with a line. This is what my Quantile regression problem, so let me do something a little different. So I may get a different slope for different quantile, and that would be my estimate of the 90th percentile Quantile regression. The idea being that it's very clear what I'm trying to get once I bin things, right? Like when I bin things, the notion of a conditional moment or a conditional quantile is very clear, and I'm just trying to capture a linear relationship with respect to X of these conditional quantities. So this is what they are conceptually. We still haven't said how to estimate those. Okay. Okay. So conceptually, and one thing I want to do is be able to write the regression function and be clear as to where the noise comes from, the uncertainty. And in OLS, we've been working with linear models, for the mean and the conditional mean for a while. There's this temptation to be able to write down the regression function as some sort of fixed element, which when we're doing OLS, would be the conditional expectation plus some noise. That's not how we're going to want to model the regression function when we're interested in the quantile regression function. Here, the idea is really that we're going to want to think of the quantile regression function as a parametrized inverse CDF. So if f of y is the CDF of y, and I give you a uniform 0, 1. How do you draw a sample of y that has the correct distribution? Yeah, you just take it in the exact. You just take the inverse, take the uniform 0, 1 and that, call that your y, and that's going to have the correct distribution. And so you can really think of wanting to do that, but for a parameterized inverse CDF. So the notation we're going to have is Q. The quantile regression at the tau quantile, I put the tau here, is the quantile regression of y. This is not an argument, this is just telling me I'm talking about the distribution of y. And then I condition on x, and this is an argument because I can change those and get the distribution for a different y. And so, exactly to your point, if I have this quantile regression function, and I stick in here my random uniform 0, 1, this is going to generate a y with the correct distribution. So this is where the randomness comes from. The randomness comes from drawing my rank uniformly at random amongst all the possible ranks. And then at that rank, the inverse CDF tells me the value that corresponds to this rank. And so when we make the linear assumption, this becomes x, because I'm conditioning on x and I'm saying that the quantile regression function is linear, x beta. And where does the u come from? Well, for every different tau, remember, I have a different slope, I have a different beta. This was x beta 0, 1, and so the u goes here. And so that's my regression function. There's no additive error term. The randomness comes from picking your quantile. And if you make the assumption that the quantile regression function is linear, which it is never, but we'll talk about why it's still okay, this is how you evaluate your regression function. But I think, yeah, the one line takeaway is that really there's this object that we're used to, the inverse distribution function, and we're parameterizing it in x. But other than that, it's acting the same way. It's eating a uniform 0, 1, and it's giving you a y with the correct distribution. Okay, any questions? Yeah. Yeah. So we're going two different ways. If we're generating the y, then we draw a uniform either at random, plug it in, get the y. If you do that 1,000 times for 1,000 different u's that were drawn uniform 0, 1, then you get 1,000 samples from the conditional distribution of y. If you estimate the quantile regression, yeah, you fix it, and then you run the quantile regression, and you do that separately. You can do it jointly if you want to make sure the lines don't cross, but you do it separately for every tau. Yeah, there is a residual term, but that is, you shouldn't think of that residual term as being what the randomness that creates the y around the expectation. Yeah. Yeah.
So something I was confused about before. So in the well-specified OLS case, right,
Yeah.
epsilon doesn't correlate with x, because that's just how this is a model assumption.
Yeah, yeah. Otherwise, it would change the conditional expectation. Yeah.
And there's something analogous here, which is like the correlation between u and x,
Yeah.
right? But I'm having like, how do you make that precise? Like, you know, I think that might come later if you think about causality or something.
Yeah, exact. You really want it exactly like you said it. You want the u to be independent of the x, regardless of which population I'm in. I'm drawing my rank in that population uniform at random. If you want to think about it delicately, then the first Chernotzkov-Hansen paper for Quantile IV goes directly at that, because the issue is that one of these x's is treatment, and you opt into treatments where you know that your u is high, that you get a good outcome. So they tackle this question directly and have all the notations for it. So that would be the place to look. But for our purposes, the way you said it is rigorous. Use independent of X. Yeah. So that's the Chernyshkov-Benson, Konachika 2004, I want to say. Yeah. Okay, now how do you estimate these things? So, yeah.
When you're setting up these way of generating the Y
Yeah.
conditional on X, just so how do I think about the restrictions that I need to impose on the Q U Y of X so that it's a legit way of generating it? I mean, it seems like analogous to the conditional distributions, I have some sort of monotonicity.
Yeah. Yeah, yeah.
But just like say, if I had never thought about this and I just like want to generate a joint of
Yeah.
X in this way
Yeah.
via this quantum function, just remind me, what are the restrictions that I need to impose on you so that I have something valid?
So the issue is going to be with the contraction function. If you're trying to use this to spit out the well, okay, think about it from the estimation perspective. So if the support is infinite and the lines are not parallel, they have to cross somewhere. So that's going to be not valid. That's a problem. And so you can impose that they don't cross, but then that of course means you need finite support. And then if you want to generate data with a contraction function that's linear, then again that means you need to have a finite support. Yeah. Which is also another reason why in this, there's no way that the contraction functions are linear, but yeah, we're gonna get there in a second. Okay, how to estimate these things? So, we had the least squares loss function for OLS. If I'm doing OLS, then I have my squared error objective. Now I'm gonna do quantile regression. So for median regression, for instance, I'm gonna have the absolute value loss. And if I have, but more generally, if I'm looking for a different quantile, then I'm going to tilt, I'm going to tilt the absolute value loss to penalize more positive errors than negative errors, so that I allow, let's say, if I want the 25th percentile, 3/4 of the errors to be positive because they're penalized by 1/3, as opposed to by 1/4, and only 1/4 of the errors to be positive. So we can do a very easy perturbation exercise to think about why that makes sense. So suppose I forget about conditioning. 1, 2, 3, 4, 5 in my set, and I'm trying to use this objective. So y1 equals 1, y2 equals 2, all the way to y5 equals 5, and I'm trying to find the median. So if this is my median, clearly is 3, and then what's the sum of penalties? The guy 1 away gets penalized by 1, the guy 2 away gets penalized by 2, and so that's I sum these, so this is 1, this is 2. I sum these to get the objective function I'm trying to minimize. If I perturb and if I try to have 2 as the median, what cost would I pay? I would pay a cost of 1 here, I would pay a cost of 1 here, a cost of 2 here, and then a cost of 3 here, so I would pay a higher cost. So clearly I'm moving away by switching this cost of 1 for this cost of 3. I'm paying a greater price. So you can kind of get very direct kindergarten-like intuition for why the check loss function is right with this perturbation exercise. Okay, so we just did it on the board for tau equals 0.5 and for the unconditional case. Right? This perturbation exercise can convince you. You can also, at home, try the same perturbation exercise with a tilted loss and see that you're going to get the quantile that you want. How would you get a conditional quantile? Well, just replace this zeta with x beta. So now I'm solving for a solution that depends on x. And that is exactly, this is naively derived, exactly the form of the problem that we're going to solve. So this is the general expression, and this is the check loss, so the absolute value tilted if I want not tau equals 0.5, let's say tau equals 0.1. And I'm implementing this n estimator in beta to get the quantile regression estimate on beta. And so that we're going to see next time is a linear program, so very easy to solve even though the viscous function is not smooth. If tau is 0.5, it visualizes back the case you probably know of the median regression. So I wanted to, we're going to spend more time talking about estimation much more rigorously via linear programming, but I do wanted to show you how do we get these fitted lines tautologically this way. You can plug this in the computer and you can solve this. And this is the object we're interested in studying.
So one other question. So with these characterizations, so that example, the kindergarten example that we did, so if I remove the 5 and I have 1, 2, 3, 4,
Yeah.
I'm looking for the uniform probability,
Yeah.
and I'm looking for the median. So that minimizer, so anything between 2 and 3 is going to be a
Yeah,
minimizer.
yeah.
So that's not picking one specific.
No, exact. Yeah. And that's going to be true more generally because that would, when we're actually doing the regression case, it would correspond to a full facet of the Pouliot, minimizing the problem. So yeah, but with continuous data, in the regression case, you almost never get multiple
If
solutions.
you were to get it, the linear program, say if I didn't know about this and I'm just trying to
Yeah.
multiply the
Yeah.
linear program, the linear program would just pick one of these things, but it probably depends on
It would tell you that you get a warning that there are maybe multiple solutions. It would pick one, and then it's actually feasible with the output of the LP to find all the solutions. A case, actually, so Yoon's a bit of an expert in that. A case of interest, the problem that Litamer brought up, is when Y is discrete, you get now it's more partial identification. Now you get like in a fundamental sense multiple solutions, and that's kind of I think it's still sort of open like exactly how to get the methodology right for that. So there are cases where there's structure either in the Y's or the X's that make it such that you get non-uniqueness. Yeah. In practice, it's never been a problem for me. Okay. So, what have we done so far? We've introduced quantile regression. We've motivated it in part with the Gary Chamberlain example, saying, look, we want this tool to get at the big picture, to get at the full conditional distribution. And we've said at a high level, but now you would know how to plug it into the computer, how to estimate this quantile regression. Now I want to study it a little bit deeply, and I still want to proceed by analogy with OLS. And I want to talk about how this reduced form estimator, when we're misspecified, which certainly we always are, is still giving us something reasonable. And that should be a criteria you always have on your mind when you're developing or using reduced form estimators. So think about the OLS, quantile regression, maximum likelihood. Okay, so a question of utmost importance for inverse problem is when we want to interpret the solution coefficients, or at the very least the regression function, is under misspecification when we can't possibly be getting the object that we're interested in because the function we're interested in is not in the class of function we're optimizing over. Are we still getting something as close to it as possible in a reasonable sense, according to a reasonable notion of distance? So we do get that with OLS, and that's certainly a very strong motivation for relying on the method for data analysis. And we're going to see that quantile regression has the same desirable property. Okay, so let's kind of first redo OLS from scratch, but in a modern way. And repeat the exercise with quantile regression. Okay, so you open undergrad textbook or even a paper, and you get presented the model that they're studying, and they're going to present you this regression function. How do you interpret the beta? Well, it depends on the assumptions on the epsilon. And oftentimes you'll get that either x are fixed or that conditional on the x's, the epsilon has mean 0. So conditional expectation 0. So what does that mean about this gender and age? What does that mean about this conditional expectation? Well, I can plug in the y. So this is being very pedantic here, but so beta naught plus g beta g plus a beta a, conditional on g and a. Sorry, that's the whole point. Well, everything is fixed except the error, and the error and this assumption has conditional expectation 0, so that's just beta naught plus g beta g plus a beta a. And so a is age, y could be, let's say, height. This could be age. So what's the problem with this expression? I mean, there's one big problem. It's not true. Right? Do you grow up linearly with age forever? It's just not true. It's just not true. But we're going to run this regression under the pretense of studying this object. So now we have existential anxiety because we're trying to estimate this object. We're gonna try to find it amongst functions of this class, and it does not have this shape. So what are we doing? You should be feel anxious now. This is the emotional point of this lecture. Okay, let's push a little bit more. So conditional expectation of height given age. Well, that's certainly not linear. Conditional expectation of income given education, same thing, you know. Elementary school, high school, master's, PhD. Maybe it's linear, maybe actually it goes a little bit faster. And when you get to PhD, sorry to tell you that. So again, it's not linear, but doesn't mean, it's not saying that this function we're after, remember we're after the conditional expectation. So it's the conditional expectation as a function of x's. We want to be able to change the x's, right? Change the age or the level of education, and have this function output us the conditional expectation of y. That function exists. It's just not linear in most applications. So if we keep looking, in fact, optimizing by running OLS for some solution that's linear, we're not getting what we're after. So what are we getting? We better know if we want to be serious about data analysis, otherwise we just don't know what we're doing. Okay, so let's think about the objects that are floating in here and get a sense of what we want, what we get, and is what we're getting close to what we want. So there's the regression function. That's the gold standard. That's what we want, right? We want the conditional expectation of y given x. This is very easy. It has a very tautological extremal characterization. It's just whatever function y tilde of x that minimizes the least square problem in population. And so it turns out that the function y tilde that's going to make this expectation of square difference as small as possible is the conditional expectation of y given x. So that's a very nice extremal characterization of what we want, and also we get our sample problem in the limit, so in population, but over an unrestricted class of functions. So we want that. What are we doing? Well, we're running a linear projection in population. So what we're doing, what we're estimating, if you will, is OLS. So that's going to be, take the X. So these are matrices, right? X transpose X inverse X transpose Y. And that's going to give me my Y hat. And of course, this is my beta hat. And so X beta hat is Y hat. Okay, so that's what I'm estimating. And what am I getting? What does this go to in the limit, right? This beta hat, we know it stabilizes, so it's going into to probability to something. What is it going to? Well, unsurprisingly, it's going to the limit problem, which is the population problem, but where you restrict yourself to minimizing over function y tilde of x that are linear. And so I could rewrite this. So the standard notation is y star, expectation star, yx, so that's Gary's notation. And this is our min, and I can put the beta directly here. Expectation in population y minus x beta square, like that. And I can write that directly as a linear function. And that's fine. Okay, so we're estimating this, we're getting this. Are we happy with that? Right? What do we want? We want the thing we're getting in the limit to be close to the thing we're hoping to study. Is it? If it's not, then we should change jobs, right? Because we're just doing silly things. Okay, so it is in kind of exactly the sense you were hoping for. So the conditional expectation, which is what you want, if you try to get it as close as possible to a linear function, what are you going to pick up? The linear function that's the closest in this L2 sense to the conditional expectation is the best linear predictor. So this is minimized at beta star. So even though we could not possibly get the conditional expectation if it's not linear, amongst linear functions, we're getting the linear function that's the closest in a very satisfying sense to the conditional expectation. This is why it makes sense to do OLS, even though the conditional expectation, the object of study, is never linear. So extremely, extremely desirable property. We have it also for, in general, for maximum likelihood with respect to the Kullback-Leibler distance. Another reason why it's reasonable to do maximum likelihood, even though the distributions are never correctly specified. And now we're going to want to ask if we get something like that for quantile regression, especially since we're really proposing it as a reduced form estimator. Okay, so the kind of table I was sketching here is here. So I just want these two slides to be well digested. So is everybody clear about the notation here? The statement, the content of the statement? Okay, all good? Okay, and here, so this is the kind of picture take home slide. So the best predictor or conditional expectation, we're trying to get it. That's the gold standard. We're doing OLS, so getting our orthogonal projection. What does that converge to? To the solution of the limiting problem, so the best linear predictor. Is this good? Well, yes. This is, given the class of function we're optimizing over, this is really what we were hoping we would get. It's the best approximation to the object of study. Yeah.
What do you think that is desirable, like this kind of interpretation? Because if you think in application at the end, like
Yeah.
it's misspecified.
Yeah. Yeah. So best does not mean good. Yeah. That's for sure. So then you can play a lot of games. So when I teach this to the master students, I kind of have a nonlinear function with coefficients you're interested in, and then when you fit the best linear approximation, you get the coefficients that flip signs, and so you can go completely crazy. But the idea is that The idea is that you need to think, I'm an applied researcher. I did my best to model this conditional expectation linearly. I'm close, but it's not in the set. So it's you know, I'm close, but I'm not in the set. The set is here. Is there a sense in which the picture you want to have, which is I'm going to solve here, is correct? Or if you're not in the set, then you're going to get like this. So you want to be rewarded for your modeling efforts, even though the function of interest is not in the set. That would be the way of pitching it. But no, but we can talk more if you're unconvinced, because I feel very strongly about this as a good property. Okay, great. Okay, we're doing very good on time. All right, so then it's equally important, especially since I'm trying to pitch to you that you should use quantile regression on par with OLS, to ask the same question. Are we getting something reasonable or complete garbage when we run linear quantile regression, given that the quantile regression function itself is certainly not linear? If the average age is not linear in X, the 10th percentile, the 90th percentile of age, of height, is certainly not linear in H. So the same pieces are showing up, right? We have our fitted values, our conditional fitted quantiles in this way, and we have population estimates. Right? We can solve for the quantile regression function in population. Trivially, this is what we're consistently estimating, whatever solves the linear quantile regression problem in population, right? Because in sample, this is a sample average, it goes to the expectation, and since things are smooth enough, the minimums also converge. So we want to know if the thing we're consistently estimating is a reasonable object. So of course, the fact that we're consistent for whatever solves the problem in population does not tell us that the linear quantile regression estimate minimizes, we know that this tells us that the linear quantile regression estimate minimizes prediction loss according to the check function, but that's not satisfying, right? We want to study the quantile regression function, so we want our linear approximation to the quantile regression function to be close to it in a reasonable sense. So what we want is not to know that we're doing good at the forecasting exercise, so to speak, but that we're doing good at the scientific exercise, that we're getting the quantile regression function. And so, are we getting that the thing we're estimating is close in a satisfying sense? So this is what we have. This is what we want. It's close in the satisfying sense, so some norm, to the thing we want. And well, one really satisfying answer would be to put a 2 here and to say that, and have this as an expectation. So what would be really satisfying would be to get the same notion of proximity as for RLS, right? If we could get that in the limit, our linear quantile regression function was as close as possible to the true quantile regression function, that would be great. That would be exactly the same property as OLS. So we're not getting that. If we were die hard on getting that, how could we? Well, we could sort of bake it in. We could, if you could get the non-parametric quantile regression estimator, so that's your proposed estimator, and say, well, actually, I would like a linear representation, then you could, in the first step, estimate non-parametrically your quantile regression function, maybe by binning the x's, and then just find, according to an L2 norm, the linear function of x that's the closest to this non-parametric estimator. And so what's going to happen here? This converges to the true quantile regression function, and you're going to get, in an L2 sense, the closest linear approximation. Then you bake in the L2 approximation, so that's very nice property of minimum distance estimators. That's nice. So in fact, the numbers I showed you before, the unionization example, that's how it was computed. So it's not unreasonable. And certainly a motivation was to get this best approximation. Yeah. Okay, so why don't we do that in practice all the time? I mean, there's something here you don't want to have to do. Yeah. Yeah, exactly. Right. There's the whole point is to get like an Regression estimator and LP, put the x's, the y's, get the beta hat be done. This requires you being able to run a non-parametric quantile regression, which is not a walk in the park. Okay. So what we're interested in is not the best approximation properties of the new estimators, the best approximation properties of the quantile regression function. So the beta that minimizes the check loss. That's the estimator that's used all over the place. That's the estimator we're going to use, so we want to know that it's reasonable. So we're interested in the properties of the linear quantile regression estimator, this linear program. That has been worked out fairly late when you think about it by Josh Engris, Victor Chernyshkov, and Ivan Fernandez-Val, and they get the best approximation result. So they're gonna tell us essentially in what sense, if any, we're minimizing the distance between what we want and what we have. And then the paper does a lot after that. Since it casts you in the Euclidean space, you get a notion of orthogonality, you get residual regression, you can talk about OVB. So at least conceptually, it's very nice. And they also do, they also get a sandwich formula for the asymptotic, it's already a sandwich, but they get large sample inference that's robust to misspecification. Okay, so this is the result. So we're getting almost what we want. So we're getting that what we're going to in the limit, right? You can put a star here if you want. We're getting that what we have in the limit is going to be, we want this difference to be small, is going to be close to the true quantile regression function according to squared error, but a weighted squared error. So it's weighted out to loss. I would say that's a perfect news. That's good news, right? These weights are not too crazy. We're closing the not quite L2 sense, weighted L2 sense. But what I want to know is not the fine details of the distance between my model and the true quantile regression function. I just want to know that in some reasonable sense, I'm as close as possible. Some reasonable notion of distance. So on first order, I think this is very good news. Right, we can put it in notation that's even more encouraging. So if I look amongst, what I'm getting in the limit is x beta star, as I was saying here. And that is the function, if I'm restricting myself to linear function, that's going to be as close as possible to the object of interest, according to some norm. Well, a norm that's a little bit weird because I'm getting weights. But one way to reassure yourself is that these weights don't fluctuate like crazy, so this is a reasonable norm. You could even expect those weights to some extent. And so we have anxiety, now we relieve the anxiety. We're getting that what we're estimating in the limit, the linear quantile regression function is as close as possible to the object of study, the true quantile regression function, in a reasonable sense. So that's the take-home message. Yeah. Yeah, I'm gonna, because I've tried to not critique them right away because I want to emphasize that the message is positive, but the next slide is going to is going to take a bit longer on the weights. Okay, but so yeah, I'll say more about the weights in a second, but I want to, this was master All good? Yeah.
Just say, suppose that I start just in a more naive way. I just really take the analog problem of the OLS, the best linear prediction problem, and I really say, well, in the population, what would be the data such that the expected value between the quantile function for a particular tau and x prime beta and all that squared, what is the data that minimizes that? Do we know what's the answer to that? Like, if I just try to solve that problem unweighted,
Oh, no. You want to like solve that problem so that you can look at it.
No, I just want to solve the problem and then look at the sample analog.
Yeah, yeah.
It's not going to be quantum regression, but
Yeah.
that seems like something I could be interested in.
So you want to write this problem in population and then do clever math and get a.
Go to the other side. If you go to the other side, yeah. So the other, yeah. So that one. So what I want to do is I want to kill the weights in the first display.
Yeah.
Omega tau.
Yeah, yeah.
Just write that problem.
Yeah.
Minimize q tau y of x.
Yeah.
X prime beta.
Yeah.
And I'm going to call these, quasi quantum regression.
Yeah, yeah.
And then just look at the sample analog.
Yeah. So the naive sample analog is the tautological sample analog is that. Can you start from the population problem with this, do clever math, and get an expression for beta that has a sample analog? That would be amazing, but I don't know. Yeah.
Is it also that maybe, for the x's that you never see, you don't care about the loss that you will incur?
Yeah, yeah, yeah.
So it makes sense to have some weights. I don't know about those ones.
Yes, that would be, but that's not what these weights are doing. Okay, so this is let's go to the weight. So this is the good news. We're reassured. We're doing the best we can within the class of linear models with respect to a notion of distance that is not too crazy. Now, if we want to go sort of second order of precision, want to complain a little bit, well, let's think about those weights. So what the authors propose is to take they work out an approximation of the weights, and they say the weights are bigger where the quantile regression. Let me just read it out to get this over. So you want more weight at x's that generate y's that are more likely to be near their true conditional quantile. So in this sense. But that's telling us that there's some approximate probabilistic interpretation. It's not clear that it's a favorable one, but that's something to read into. But then, so Blaise is not here right now, but we're talking about this paper, and he had an excellent point. So these weights, and here we're a little more critical, and I think people have thought about that a lot. So, okay, the formula, this monster formula is a little bit disgusting, so that's why the authors gave this more concise approximation. But it hides something important. This is a function of the degree of misspecification, right? It's comparing x beta star and the true quantile regression function. We're given the degree of misspecification. This is fine. These weights are still going to come in fairly stable, and we're going to try to be as close as possible to the true quantile regression function in some weighted L2 sense. But then if I want to do the slightly different exercise of comparing the distance between my linear approximation and the true quantile regression function for different models, I can't really do it anymore because the notion of distance changes. So in particular, I may have a model that's more specified in a kind of sense that's fixed across model and more reasonable to me, but for which the distance becomes a lot more the weighted distance becomes a lot more forgiving because the weight changes. So the fact that the distance is different for different models makes it that I can't really compare models. And in fact, it means that directly doing model selection in sample according to this check class is maybe not completely warranted. Right? That's very interesting. So this, nobody, I think, has really studied that, but there's something to do there. Maybe it doesn't make sense to pick between models by looking in sample at your check loss. Maybe you really have to cross-validate. And that's an extremely popular question in classification, so it might be interesting there might be a publication payoff to looking at that here. Okay, so so again, this is kind of, we're getting in the nitty-gritty. We're criticizing, but I'm not trying to push away the positive message. The main message is a positive one. We're very, very happy about getting a best approximation, even though we're never correctly specified. Okay, so kind of wrapping up, I just want to make some quick points about inference, because you're going to go and you're going to do inference. Oftentimes you're going to do huge large sample distribution theory. There's some little quirks, and I want to talk about interpretation a little bit more, and then we'll be able to wrap up. Okay, so we have, well, there should be a hat here. So we have CLTs for the regression coefficient. We get the typical sandwich formula, inversion, inverse Hessian, variance of the score, inverse Hessian. And then we have little complications, because we can look at these objects. So the variance of the score is fine, but this Hessian, it looks like the expectation of the gram matrix, and then the density of the errors for the y minus sigma beta, which we were talking about earlier, conditional on x. And even if you're willing to make this very strong assumption that the errors, the conditional solution of the errors is the same as the unconditional solution, which really means that your fitted lines at different quantiles are parallel, so it's kind of making quantile regression moves. So it's a very, very strong assumption. That would allow you, of course, to plot the density outside of the expectation. This assumption is used in many places. Inference seems to be robust to it, but in any case, whether the density is here or here, in some sense, you're going to have to deal with non-parametric density estimation. So you're typically going to keep it as a sum end in the sample average that approximates this expectation, but there's still a notion of bandwidth that's going to come in for estimating this density. So that at a very superficial level, think of estimating the density. It's non-parametric density estimation. You need to pick a bandwidth. In fact, we're going to, we're going to be a little bit more clever about it, but we're still going to need to pick a bandwidth. So let's look at support vector regression. It's a median regression is a special case of that. And if I'm just proceeding with the wall estimator, so doing inference on beta hat, estimating the asymptotic variance, and building your usual confidence interval that way. In building the asymptotic variance, I need to pick a tuning parameter because I need to estimate this non-parametric distribution function. And so this is a menu of a priori reasonable bandwidth values, and this is coverage under the norm. So the nominal level is 0.9, and I can get essentially any coverage between 1 and 0.25 by picking the bandwidth, which means I can give you confidence intervals of the width you want. I can cheat. So that's not good, because then we're not going to believe the output. If someone wants this estimate to look precise, just pick a different bandwidth and report very small confidence intervals. So we don't like that. But we can get this line. And that's with the standard large sample approach. So I just want to name it to you, present it to you so that you know about it. So we're not going to want to estimate beta hat directly because we don't want to deal with the asymptotic variance of beta hat because we don't know how to estimate it in a stable way. So we're going to invert a different test. How do we do that? Well, an easy way of doing that is a kind of standard recipe would be, I'm going to invert the test. So how do I run the test? Let's say I want a confidence interval for beta 2. Suppose beta 2 is equal to beta 2 naught. That's my null hypothesis. Build the test statistic this way. So concentrate out x2 beta 2 from y. If I get the right value of beta 2, there should be very little x2 variation left in here. Regress that on x1, and that's going to produce short residuals from that regression. If indeed I took out all of the x2 variation, So this is a vector. The inner product of these errors with x2 is going to be small under the null. But if instead of taking out the correct value of beta 2, which maybe was 0 or 1, I put beta 2 1 million here, then I'm going to have a lot of x2 variation in the residuals. And so this is going to be large under the alternative. So that's a test statistic that's going to have power for the obvious reasons. I can also take the sign of this. This is still going to covary or not with the x2 depending on whether I'm under the null or not. And if I do that, I can demean and divide by the standard deviations. I can studentize. This object is going to have a very well-behaved limiting distribution. It's going to be normal 0, 1. And the variance of the unstudentized object, so the variance I need to estimate, is tractable. And in particular, under this homoscedasticity assumption, it's going to be completely pivotal with respect to the density, so I won't have to do any non-parametric density estimation to do. Even without assuming that, you see how this black line is not completely stable in the bandwidth. Even if I do not make the homoscedasticity assumptions, on the general assumptions, I'm much more robust to bandwidth selection, extremely stable to bandwidth selection. It just is the nice property of taking this object as the test statistic. It also turns out that this is going to correspond to the dual feasibility condition for x2, so it embeds inference very nicely in the dual linear programming structure of Quantile regression. But it's really this plot that is the motivation that made this approach to a large sample inference standard for Quantile regression. So this is, when you run R, this is how your confidence intervals come out, and that's why they're not symmetric, because you're not doing beta hat plus or minus, you're really inverting a test. Okay, when you estimate your beta hat tau at multiple taus, you often want to present it beta hat tau versus tau. When you want to make comparisons across tau, across quantile, and see that they're significantly different, typically you want bands. We haven't talked about jointly valid inference, so bands that are valid uniformly, not just pointwise. So these are easy to get. The theory is complete for that. The last point I wanted to make, and this is kind of a very simple point, but people make the mistake so often that it's worth specifying. So when you talk about, suppose you believe you have a causal effect because you have randomly assigned treatment, and you have before treatment and after treatment, and have x beta say 0.1 and x beta 0.9. And what are we saying here? We're saying that, so this is the 10th percentile. We're saying that after treatment, the 10th percentile moved from this level to this level, and so people, the state of the distribution has improved in its outcomes on measure of health by some. So it does not mean that the person on the 10th percentile improved by this much. Even if we have panel, this guy could be here now. It's really about the quantile of the distribution, not who is on that quantile. The people, even if it's a panel, could reshuffle over time. What we're picking out is really something about the shape of the distribution, the conditional heteroscedasticity, and that's important to keep in mind. I think just when verbally people make that mistake quite a bit. Okay, so wrapping up. So the quantile regression reveals aspects of the conditional distribution that OLS misses. I like the unionization example, extremely compelling in that dimension. User-friendly inference obtained. So for large sample inference, this is called regression ring score inference. So you get very, very stable large sample inference. Confidence intervals are not necessarily symmetric, but I think we can emotionally get over that. You can bootstrap. You can bootstrap the quantile regression, so that's available too. You're gonna solve an LP, 1,000 times, that's fine. That still will be very fast. Interpretation at large may be a bit challenging, so this is kind of, I think somehow there seems to be a little bit of hesitation when thinking about the effect on the quantile as opposed to the effect on the mean, the average effect. I think it's not fundamentally more complicated. I just think people feel more comfortable, like non-technical people maybe feel more comfortable talking about the average effect without understanding what it means than they are about talking about the effect on the quantile, which is also maybe that lay people maybe don't know what the quantile is. But that might just mean that there's some work to do into like visual representation or how to articulate findings about the quantile when you're writing a newspaper article for lay people. But so there might be a bit of a communication challenge, but certainly in anything near academic research, that's not a problem. That's not an obstacle. I think the only obstacle is ourselves. We just need to run the quantile regression. The software is there. Any serious supply people knows how to interpret it. We just kind of, I think as a community, need to make a bit of a push. Yeah, okay, so that's it. So I hope I've convinced you that you can access more information by running the quantile regression at different quantiles as opposed to just the OLS. And so this kind of, today was a bit of an applied pitch, a pitch for applying quantile regression. Tomorrow we'll go deeper into the machinery. I think in terms of regression analysts, there's really a desire to understand the closed form-ish expression for beta hat. It's so satisfying in OLS, right? This orthogonal projection story. Can we get something there? And then we're going to see something fascinating. The same way linear algebra reveals the structure of the OLS problem, linear programming, the duality of linear programming, in particular linear program duality, is going to reveal and shed light on the structure of quantile regression, and in particular the closed form for the beta hat. So that's going to be the game plan for tomorrow. If you get a chance to skim the proof in your notes for the closed form for beta hat, that might make the lecture tomorrow easier. Yeah.
So everything was fine until you did the example.
Yeah.
So if, like you say that, this person is allowed to start from the low quantile in the initial distribution, and after he can jump to a high quantile in the final distribution. So this means that the other ways it can happen too. So you have in the initial quantile, in the initial distribution, the people in the high quantile, and you can drop. So if we assume, let's assume first that it's rank preserving. So before and after. So if it's rank preserving, like treatment in each quintile is positive.
Yeah.
But if it's not rank preserving, this means that you have both negative and positive effect. So how can you distinguish from?
You can, right? This is if you add rank invariance, then this guy moves here, and.
But in reality, like the certain case where you don't have rank preservation, you have a much larger heterogeneity in the effect of the treatment.
Yeah. But so there are two parts. So if you're interested in that, like were there positive effect, negative effect, then you can go to the distribution of the treatment effect, and so that would be so Freshev bounds, for instance, on this distribution function of the treatment effect. And so we have like two experts here of that problem. So Amkar, if you want to know how to compute that, Amkar can tell you. Okay, so that's one answer. Now, should you be interested in that? I want to help people who are worse off. I don't care who is worse off. I want to help I want to make the bottom of the distribution better. So for policy purposes, I don't need this rank invariance assumption.
Okay, so basically it's not describing the distribution of treatment effect, which is something that could be completely different from what's.
So it's the treatment effect on the quantile. But my point is that I think sometimes there's a reflex of thinking that is this qualifying because you don't know what happens to the person on the quantile. I don't really care. I'm a policymaker. Whoever is the poor person, I want to make sure they're richer.
Okay.
Yeah. That's it. Okay, thanks. Yeah, any other? Yeah.
So when you were talking about the regression ring score, you gave us the sort of intuitive picture.
Yeah.
The epsilon hat times the x.
Yeah, so I cheated a little bit, right? So this, I took the sign of the epsilon hat, but really is the variables that are going to come out of the dual, all but, let's say there are p regressors, all but p regressors, all but p of them are going to have this form. Yeah.
I wanted to ask, that step going from the epsilon times x to the sign of epsilon times
Yeah.
x, I'm sure we'll talk about it tomorrow when we learn about feasibility and things
Yeah.
like that, but without knowing anything about linear programming, is
Yeah.
there any intuition for why we would design a test statistic that uses the sign?
Yeah.
As opposed to
So I guess there's a two-part answer. Like either you're like living inside the matrix and you can see like 20 steps ahead, and you knew that this would give you a nice asymptotic variance expression that you could estimate well. Other than that, not recognizing. Other than that, you could think that, oh, if I take signs here, this becomes 0, 1, and this is going to look like a rank test. And then you can have hope that at least for nulls on the full vector, this procedure is going to have exact validity properties. We're going to touch upon that in the third and fourth lecture. But other than that, no, this is not only the dual feasibility condition, this is essentially rewriting the objective function. So you're using the first order condition. You're testing the first order condition, which is a very naive way to build a test statistic. Because the objective function for L square, for OLS is error square. So first order condition is linear in X. Now our objective function is L1, and so one derivative below, instead of having as for OLS an orthogonality condition of this kind, since you differentiated or something that was linear, you're getting an indicator. You're getting an indicator on the error, basically, on the sign of the error. So there are many ways to get directly at this by thinking about what you want to test. In terms of anticipating a good test, it's kind of, I mean, historically they came up with this for the reason I said, like it's the first order condition, it's your dual feasibility condition, and it looks like a rank test. Historically, the reason why it stayed is because the asymptotic variance is much easier to estimate. So it was not anticipated. So it's a good question. The reason it stayed was not the motivating reason. Yeah. Okay. Any other question? Yeah.
So I was trying to understand the relation between that inverse Chern-Trickler Fernandez and the one you proposed in the beginning where there's a check function, the objective function.
Yeah.
Since check function doesn't really show up in their objective function.
No. Sorry. Yeah.
Does that mean we?
If I want to minimize the L2 distance between my regression function and the true quantile regression function, I can do minimum distance this way. So this is saying if you want to minimize L2 distance, this is an estimator you can use, and we don't really want to use estimator because it requires non-parametric density estimation. Okay, now let's go the other way. Given that I am using quantile regression, minimizing the check loss, what am I getting? So Angus, Chernuskov, Fernandez-Val, they start by saying, I'm running quantile regression, minimizing the check loss. What am I getting? And we're getting this. So you're not seeing the check loss in their characterization, but they are starting from the check loss. If I minimize the check loss, what do I get? I get in the limit a regression function with this extremal representation. It's minimizing distance to the true regression function in exactly that sense. But we didn't know before what we were getting. They worked it out, and this is what it looks like.
It's important that we incorporate this weight.
It's what?
Is it important that we incorporate this weight calculation?
Well, you don't have a choice. When you run quantile regression, this is what you're getting.
So does that mean in practice we're also calculating this weight?
No. No. In practice, you're minimizing. So in practice, you're minimizing this, but this is the distance between the data and x beta. And that's going to tell me also that in the limit, 1 over n here, this is going to become an expectation, and I'm going to minimize in the population the distance between the y outcomes and my x beta expectation today. Because I'm doing good at forecasting. But I want to know if I'm getting close to the conditional expectation. So they're saying, whatever this converges to, can I write it as minimizing some difference with the true quantile regression function? And it's that. And again, it's not something you choose. It is what this is minimizing. Yeah.
Regarding the point of the misclassification, you mentioned like the weights here depend on like a certain type of model, like a certain degree of misclassification
Yeah.
is needed for model selection. I wonder if there's like other estimators where we can do more robust degrees of misclassification. Is that the question?
Yeah, it's a great question. So I mean that's my kind of homework assignment here. I mean I think it's worth thinking about, yeah, because we wouldn't have that issue if we did the minimum distance, because by design we're minimizing unweighted L2. Okay, so that's one estimator I know. The other estimator I know is quantile regression, and then we're getting this issue. So yes, there's motivation for pushing farther exactly your question. I don't know. I don't think we know how to do that. Yeah. But somehow, then you need to think about the deliverable, because somehow you're not gonna make everybody switch from quantile regression to something else because of this, admittedly like third order point. But it's still important. So is there something we can? Is there a point to make, or is there a clarification to make about those weights? The solution is easy, right? If you're comparing models, you can cross validate according to whatever notion of error you want. But maybe even just formalizing that would be interesting. Yeah.
So in practice, Guillaume, I got a wrong one of these things.
Yeah.
You open it, so like apologies, but so do you just set up a grid of values of tau? Is that how it works?
Yeah.
Set up a grid of values of tau and then
Yeah.
you do the linear programming for
Yeah.
these values of tau?
Yeah, exact. So there's a paper, like very, very like nerdy paper about computing the number of different values that beta hat can take. So even if you wanted all the values, there's only finitely many.
Yeah, because I was going to ask you about that. These things somehow,
Yeah.
you should have some interpolation.
Yeah.
Because the data
Yeah.
right?
Yeah, exact.
So, but there's a paper about that.
There's a paper that goes through the exercise of like saying, I mean, in the linear programming structure, it's clear where you switch. He has a fairly old paper. I think it sits on that too, but he gets the number of different beta hat values that you could get. Yeah.
And then so, is there any restrictions on the shapes of the data that you can get, or
Yeah.
anything goes?
So it's very easy to add the non-crossing restriction. That's a linear condition. So you stay in an LP, and you just add this condition, and then you basically, let's say you have 20 taus, you solve for the 20 taus at the same time. If you don't have non-crossing condition, you're just solving 20 LP separately. If you have non-crossing conditions, then it becomes one bigger LP, but it still runs fast.
For the standard implementation, you don't have that condition, right? You're solving for these things separately.
Yeah. So I don't know for R packages and side packages if you have the non-crossing condition, but I would suspect there's an R package, and it's pretty fast to write down, like you're like in Gurubi. Yeah. So I mean, Abla is going to be here, so he also knows a lot about, and actually Alfred, but he's not here this year, about like resorting, like reordering the quantiles ex post. So I don't know a lot about that, but that's the properties of that are known, and basically it's fine to do it. Is the message? Yeah.
And then lastly, the only thing is do you know if anyone has done this fully Bayesian? Like, you start with
Yeah.
example that you described, Q of U, Y,
Yeah.
X, and you put a prior
Yeah.
distance, and then you just
Yeah.
do probably something fancy because
Yeah.
you
I think this is where so maybe Pierre knows, this is where the Laplace distribution I think comes up. So yes, there's there.
Who stopped this? Do you know?
I forget, but I know they've I know that for some reason it connects with the tilted exponential literature. So it was hot for a little bit, but yeah, I can find the references, but I don't remember.
That's perfect.
Yeah.
Thank you.
Yeah.
So this is a question that was brought up a few times of what if we wanted to take the minimum distance estimator more seriously? What can we learn about it? I'm wondering, these weights show up in so we have this, we're trying to minimize the expected check loss in the population and make sure that it can be written in a way that tells you that y minus x prime beta, you're trying to minimize the norm of that, some norm of it. And I'm trying to think about, in the OLS case, why is it the case that, there's a degree of misspecification in the same way in quantile regression? And if I remember correctly, the reason why the best linear approximation and the best linear predictor happen to be the same is that they only differ by a constant in their objective, and that constant doesn't matter, and so
Yeah.
the OLS, sorry, the solution to the best linear approximation problem is the same as the solution to
The proof you're saying the proof for minimizing this to minimizing is very short.
right.
Basically. Yeah.
Right, and it comes from the difference between y and expectation
Yeah.
and y given x.
Yeah.
And I'm trying to think if there's something, if that proof strategy can be used to better understand the minimum distance estimator and think about how y might differ from the quantile function of y given x.
Oh, but in the minimum distance it's even more trivial because you're starting from here and you want to get here.
So then, does that mean that whatever solves the minimum distance problem is also going to be the one that solves
This. Yes, because the minimum distance problem is using the simple analog of this objective as its objective. You're minimizing in beta, but instead of having the constraint expectation, you have something that converges to the constraint expectation.
Sorry, I'm trying to draw a parallel between the first line and the second line.
Right. So what are you calling the minimum
quantile.
distance?
Sorry?
What are you calling the minimum distance estimator then?
Instead of expectation of y given x, you have quantile function of y given x.
Yeah.
And I want to compare that with expectation of y minus x beta and understand, like, why is it the case that these weights show up here but not in
Oh yeah. Okay, so there's no minimum. So minimum distance, I mean like the estimator where you're trying to minimize in sample the distance between x beta and some non-parametric estimate. So we're not talking about that. We're talking about why is it that when we're starting from here, and we're trying to get to somewhere like here, we're not getting to that, but to the
So I think that's one way to phrase my problem. But
Yeah.
I think there's other contrasts we can make. So here using the check loss, and then you're comparing that to that weighted L2 norm. But I think you could also think about the unweighted L2 norm between the quantile function and x beta, and compare that to expectation of y minus x beta squared. We know those two things are different.
yeah.
And I wanted to understand in what sense are they different. That difference doesn't matter for OLS, but why would it matter for quantile regression? I'm just trying to get a better sense as to why that is. I can also ask after.
Yeah, because the difference is I can minimize this, I get the limiting object of quantile regression, I minimize this, I get the best linear predictor. After that, after that, yeah, I think there's just I'm not sure what kind of interesting comparisons would come up. Yeah, we can talk about it more. But yeah, so the point just so that everybody's on board is that arg min beta of this is equal to arg min beta of this, and separately arg min beta of this is equal to the arg min beta of this. And yeah, I'm not sure. Yeah, I'm not sure. We could look into how, like, so looking at the difference between these two. But the proof for this is not super long either. So I think that then you know everything there is to know once you have the path from this to this, the path from this to this, and you can compare. Yeah. Okay. Last question. All right. Okay. We're just right on time. Perfect. Thank you so much for your attention, and then see you later. Yeah. Thank you.